Okay, so I just wanted to do a brief overview of transformations in case this is something that you guys were struggling with at all. I know we've seen it a lot, but again, just a reminder so that we don't forget. So basically, in general, I'm going to use function notation here too, because I saw that a lot of you guys struggle with that on your weekly reviews. So I'm going to go through the types of transformations and I'm going to focus on this function f of x, meaning I'm not saying it's a square root or a quadratic. I'm just saying it's a function. Okay. So reflections are basically where we see multiplication by a negative. And that means there's two ways that can happen. That the y value can get multiplied by a negative. So that would look like the negative multiplying outside of the entire function, like in the a position, or the x value can get multiplied by a negative. And so that means the negative is multiplying the x within whatever function type it is, like a b value in our equation. So this one is kind of like an a value. This one is more like it's in a b value position. Okay. This would be our reflection over the x-axis, because even though it's changing a y value, a change in y value would flip something over the x-axis. And this would be the reflection over the y-axis. So then we're going to look at translations or shifting, okay? So we can, this is basically adding or subtracting a value. And so we could see that in two ways. We could see the entire function have something being added outside of the function. Okay, that's like our k position. Or we could see something being added or subtracted within our function. So that would be more like our h function. And so k here is a shift up or down because it's affecting the y value, whereas h is our shift left or right because it's affecting our x value. Okay. And then we saw compressions or stretches. And for the compressions or stretches, we basically saw these where we were multiplying by a different number value other than 1. So when we were multiplying by a negative, we called it a reflection. Okay. But this would be a different number value. So it could be a number multiplying the entire function. And so this would be vertical when it's that a value. And it could be a stretch, or it could be a compression. A stretch would be something like 2 times f of x, and a compression would be something like 1/2 times f of x. The other way that you could see something get multiplied by a number is that the x value is getting multiplied by a number. Sorry, that was my son running down the hallway. That the x value is getting multiplied by a number, and this is going to be a horizontal stretch or compression. And if you remember, we saw a lot of graphical evidence of how these actually work. We studied them in depthly, and what we saw were these conclusions. So I'm just giving you the conclusions here for review, is that when there was a stretch, you actually saw a number smaller than 1 in your equation, like a 1/2 times x, okay? And yet that actually doubles the distance on the graph, which is why it looks like a stretch. And if you had seen a 2 multiplying x, that would actually be a compression because the way it reacts to the distance on the graph is that it actually makes the distance shorter. So in general, that's like a review of your different transformations and kind of seeing them in that function notation you guys are struggling with a little bit. So now we're going to look at trying to rewrite one. You guys have had this on the last couple weekly reviews, but people were struggling with it. So we're just going to work on it. So we're going to write a function g of x. That means you're writing something that says g of x equals, and it says it transforms f of x. So that means everything it does to this original f of x function. So like if it has any horizontal changes, those things will be marked in here with the x like we did above. And if it has any vertical changes, we'll see those things happen beyond the function, kind of before and after it, where we write the numbers instead of within the function with x. So then I'm going to read each of the things that happens and kind of translate what that means. So right here I have a reflection, which we said was multiplying by a negative, and it's over the x-axis. So it's actually a vertical change, which means it won't be happening to x necessarily, but more to y. So I would see that negative out here in the function. The next thing that I see is I see a horizontal. So this is definitely going to be happening to x, where the last transformation we talked about was happening to the y values. And it's a horizontal stretch by 3. So remember, this comes with the b value, but the horizontal one was tricky. It says stretched by 3, but that means we expect to see a 1/3 as a b value in our equation. So that's going to show up in here like this. Okay. We also have a horizontal, so again, this will happen to x, shift left 5. So that tells me h is -5. But again, remember, the format of our equation is to have a b value and then x minus h all within the function. So here, this would say x minus -5, which ends up looking like x plus 5. And notice I was really careful to use these parentheses right here. If I don't use those, then I'm not really writing the correct value here, because it will look like that value was multiplied by 1/3, and that hasn't happened yet. Then I have a vertical stretch. So vertical means it's going to be happening to y, a stretch by 2. And that tells me the a value is 2. And it was already negative because of the reflection. So it's going to be a -2 in that a position. And then a vertical, meaning it's happening outside the function to the y values. A shift down 1, meaning that k is -1. So I'll see my -1 right here. So that's one way to write the answer. You could write the expression within the function in here a little bit differently, but you do have to make sure you still do it correctly. If you didn't write parentheses in there, it would look like this. In there, you'd have 1/3 x, but this number would also have to say 5/3 instead of 5 in order to be the correct transformations that it talked about in that problem. Okay. Now, for those of you that struggle with taking this transformation information and helping us graph, I'm going to show you using the table for the square root function, but not actually make the graph. And then I'm going to go through one greatest integer function graph. It really does the transformations visually very nicely, but we don't really use a table for that one. So I wanted you to be able to see the table as well, which is why I'm just walking through the square root function. So first thing is that you really need to write it in that one format. You really are going to have to write it, since this is a square root function, like this. This is the only way we've studied the function. So you can write it lots of other ways, but when you're writing it those other ways, you're not actually seeing the effects that the numbers have on the graph in the same way that you've studied it. So if you want to assume that something stretches something by 2 or reflects something or shifts something, you really have to have it written in this format. Okay, so this means I need to have a 3 separated from the x minus h quantity. So I need to write the equivalent of 3x minus 12, but with the 3 factored out of that quantity. So I have 3 times x minus 4. Okay, now that we have it written in the right format, we're going to think about the parent function always first. So we usually make the table of values. Because this is one is square root, the values are real select that we choose, because we're specifically choosing things close to the beginning of the function at 0 that are easy to calculate in a square root. And then remember each thing that's happening here. Okay, first of all, let me mark everything in blue that's a vertical transformation. These things are contributing to vertical transformations. This is going to reflect over the x-axis, so it's going to change the sign of y. And this is going to be a vertical stretch. So it's going to multiply the y values by 2 and double them. So y values are getting multiplied by 2 and their sign changed. And this is a vertical shift up 7. So all the y values are going to move up 7. We then look at the horizontal ones, and remember they are the correct numbers in the equation, but they mean something different on the graph. So this 3 here as a b value doesn't actually mean a horizontal stretch. It means a horizontal compression. So we actually see it getting multiplied by 1/3. And then our H value is actually positive 4 here, shifting things to the right 4. And then we go through and we change all those X values by those differences that we're going to make their distances by through these transformations. So like 0 used to sit right on the Y-axis at as X value of 0 units away from 0, and it will now be 4 units away from 0. 1 used to be 1 unit horizontally away from 0. Now when we plug that in with the compression and the shift, it'll be 4 1/3. 4 used to be 4 units away from 0. Now when we plug that in, that would be 5 1/3. And then 9 used to be 9 units away from 0 in the parent function. But here, 9 times 1/3 will be 3 plus 4 is 7. 7 units away from 0. Then we would go through and do the same thing to the Y coordinates. We're looking at those and how high they are. So this one was at 0, but now we'll be at 7. This was at 1, so negative 2 times 1 is negative 2, plus 7 is 5. This was 2 units vertically in distance, and now 2 times negative 2 would be negative 4, plus 7 would be 3. And then here, 3 units, we'd have negative 6 plus 7, which would be 1. And then we would plot those points. And with square root, you really need to make sure you keep track of the end point, since it has a end point and doesn't continue in both directions. I'm not going to graph that one. Instead, I'm actually going to graph a greatest integer function, because with the greatest integer function, we actually didn't make a table. So it's kind of a pro and a con. You have to know a little more about the graph and really understand the transformations to get the graph done. But then it really shows each transformation separately, which is kind of nice if you need to demonstrate it again. So the first thing I'm going to do again is rewrite this function in that format that we were talking about and really get that x minus h portion how I need it. So this was a 1 here. When you factor a 1/3 out of it, that will become a 3. So what I have here, first I'm going to acknowledge some of this horizontal stuff. So I have here a horizontal reflection. So for greatest integer function graph, in my head, I really think about the parent looking like this, where this is like my start point, and the steps are 1 unit long to the right, and then they go 1 unit up. And then I need to really think about, like, what does that look like when I do this reflection? And so when I reflect here, because this is a horizontal reflection, it's a reflection over the y-axis. That means that start point stays right there, but these points that went to the right are now reflected and go over here to the left. And this other step would end up looking like this if we folded the paper over and reflected it. So it no longer looks like this, and I look like I'm going to start here, draw the step to the left, and then go up to the next step. So now if I just have a starting point of where to start and what that step looks like, the lengths and the distances apart, I should be able to get going. So what I see, I'm going to give myself an x and y axis first now that I have an idea of what's happening. So we have this. So first I want a starting point, so I'm kind of looking for that hk value. So my h here is 3 and my k is 4. That's where that starting point is going to be shifted instead of 0, 0. So I'm looking at the point 3, 4. So that would be right there. And that's that starting point or that end point. Now I'm going to draw the step towards the left, that direction. And then how long of a step is it? Well, this was my horizontal stretch or compression here, and it's actually a stretch by 3. Remember, B is 1/3, but that actually becomes a stretch by 3. That means instead of being 1 unit long, the step size just got tripled, and it's going to be 3 units long. So it's actually going to go all the way back to the axis here, because that's 3 units on my axis, and there's that step. Okay. Now I need to know how far apart the steps are. And they are 2 units apart vertically. So I'd want to go 2 units up, which would be here. And I would again draw a step that's 3 units long. Once you have those steps laid out, you can then continue the pattern. So I'm going to continue it where there's room on my graph, which would mean to go in this direction. 1, 2, and it would be about there. And there's what my steps would look like using those transformations. And so you can really see them here looking at this original parent function we had for the step graph, you can visually see the reflection in the way that the steps go. You can see the vertical stretch because this distance they are apart is now 2. You can see the horizontal stretch because the steps are much longer horizontally, and you can find that position of 3, 4 on here as a starting point. So hopefully that helps review your transformations visually, and then you saw numerically how we can take care of our transformations with our charts like we do often, and then using function notation, and just a general idea of what those are, all of the different transformations.